Hi, I'm Tim, and I will present our paper Learning to Participate Through Trading of Reward Shares. I will quickly first motivate our research, then I will present our experiments in two different multi-agent reinforcement learning domains, and finally I will conclude the presentation and give a brief outlook. Individuals often prefer to possess multiple assets to be diversified. So, for instance, Tim Cook, the CEO of Apple, can essentially influence the success of his own company, but he still prefers to also own assets such as crypto and other stocks in addition to his Apple stocks. The two statements on the slide highlight that selling shares of an asset that individuals can influence to some extent and buying other assets in addition to them that are influenced by external factors can be beneficial for individuals. Now, the question arises whether this is transferable to agents in a multi-agent reinforcement learning framework. The idea is that agents could be diversified by owning shares of other agents' rewards, and then they would participate in the success and failure of these others. By doing so, they could lower the risk of terrible outcomes, and the participation can be regarded as a form of insurance and a possible enabler of cooperation of multiple agents. One of the challenges in multi-agent reinforcement learning is to align and then coordinate the goals of different agents. In decentralized models, agents often tend to optimize only their own rewards without considering the impact of their actions on the other agents. This then leads to a social dilemma in which selfish behavior leads to low individual and aggregate utility. As this is not wanted, there are some proposed solutions, such as extrinsic incentives like reward or punishment mechanisms, or using intrinsic incentives such as reciprocity and equity aversion or altruism. Our idea is to reach a socially optimal equilibrium by letting the agents participate in the rewards of the other agents. This would minimize the agent's risk exposure, and additionally, this diversity may also be a way of making machine learning algorithms more resilient and robust. The first domain that we look at in our paper is the prisoner's dilemma, where the dominant strategy of both agents is to not cooperate, so they both defect. But if there's a sort of participation in each other's payoffs, there could be cooperation, and cooperation could actually become the dominant strategy. So in this example that you see here, initially both agents defect, so there's a social dilemma, but then if there's an equal distribution of the individual rewards, it actually becomes dominant to cooperate. And as you can see here in the picture, this could lead to mutual cooperation. Here we see the iterative prisoner's dilemma. So instead of only playing this game once, it's repeated over multiple episodes. And the action space here consists of the two actions cooperate and defect. So both of the agents, or all of the agents, if there are more than two agents, can choose either of them. And there are four states, namely mutual cooperation, mutual defection, and a combination of defection and cooperation, in which one of both agents defects and the other cooperates. So there's an action tuple consisting of both agents' actions, which determines the next state as prime. Whenever there's a transition from S to S prime, the agents receive a reward depending on their actions and the corresponding states. A strategy vector describes the probabilities in which an agent chooses to cooperate in each of the states. This also implicitly describes the probability of defection, which would be 1 minus the probability of cooperation. So as a first step, we created the simulation of our participation idea. So in each episode, the agents can obtain a small share in the other agents' rewards, and the prices are set and updated automatically according to the fair predicted future rewards, so that all of the agents decide to always obtain an additional share in the other agents' rewards. We kept the maximal participation at 50%, at which point the individual rewards are equally distributed between the agents. So both agents only hold shares of their own rewards at the beginning, and there's initially no cooperation, so both of them defect, but there's cooperation as soon as the agents have a sufficient share in each other's rewards. In our actual multi-agent reinforcement learning models, we used the implementation from the Leo paper, but instead of allowing the agents to make payments to incentivize the other agents to actually cooperate, we use this participation mechanism. We then ran a couple of experiments to see how participation can influence this social dilemma and if cooperation is enabled by the possibility of participating in other agents' rewards. So this is the base implementation in which there is no trade and thus there's also no participation. So we would expect if the agents just choose randomly between their actions that they would receive on average a reward of minus 1.5, because the rewards for the four possible states are minus 1, 0, minus 3, and minus 2. So by summing them up and dividing them by 4, you get to minus 1.5, and each of the actions should be performed equally often in each of the states because it's random, and then the aggregated or accumulated rewards should be minus 3. And as you can see at the start, it's actually minus 3, so they act randomly. But if the agents instead learn to maintain a cooperative equilibrium in which they both cooperate, this individual reward should then converge to minus 1 for each of them. So accumulated, this should be minus 2. But as we know, according to a theory, defection should be dominant in this classical implementation, and then the individual reward should be minus 2, and accumulated for both of them, it should be minus 4. And what we can see in this plot here is that indeed the implementation without participation shares leads to a stable equilibrium in which both of the agents defect, and the accumulated rewards converge to minus 4. In the second implementation, we have an equal distribution of individual rewards, which means that all individual rewards are first summed up and then divided by the number of agents so that all of them receive the mean reward. So what remains the same is the actions and states, but in terms of the convergence, there's now a stable equilibrium where both agents cooperate, so the cumulative reward converges to minus 2. Now in the third implementation, there's an extension because we include the possibility of trading participation shares. So all agents receive a reward according to their participation shares, and initially at the beginning of the games they do not participate in the other agents' rewards and only possess 100% of their own shares. Now the actions are now different because they also have a trading component, so they can be regarded as a 3-tuple consisting of the environmental action, which we also had before, but then also an increase or the decision to increase the proportion of own rewards and the decision to increase the proportion of other agents' rewards. And the idea is that a trade only occurs if all of the agents want this to happen. So all of them need to agree to, for example, increase the share in their own rewards. There are now 36 states. So the environment actions times the proportion of own shares times the trading factor, which is increase the number of shares or decrease the number of shares or leaving it at the same. There's now also a convergence to a stable equilibrium. So, and what's interesting, they again cooperate. There's a cumulative reward which converges to -2. So having this trading decision enables cooperation. In the final implementation, we made sure that trading smaller participation shares also leads to cooperation, which was the case. Cleanup is a more complex domain. We will present our results for 3 agents. So it's an intertemporal social dilemma because the agents have to balance short-term individual incentives against long-term collective interests. They would like to go to the right side of the map to collect apples to get rewards. However, as the waste level on the left of the map increases and approaches an exhaustion threshold, the apple yield rate drops linearly to 0. So some of the agents should go to the left side of the map to clear waste. In the first implementation, there's no participation. The cumulative reward of all agents doesn't increase over the number of episodes, there's no learning effect, and none of the agents learns to eliminate waste. In the final episodes, the agents still do not act according to a clear strategy, and there's a certain randomness of the behavior that the agents learn. Interestingly, this is also the case when we use an implementation of Leo from another paper. So the cumulative reward of all agents again doesn't increase when we have 3 agents, and this questions the applicability of Leo to more complex scenarios. If we instead look at an implementation with an even distribution of individual rewards, this changes. The state and action space is unchanged, but the agents successfully divide their tasks. So some of them start clearing the waste, and there's a variation in learned strategies between the experiments, but the strategies remain stable within the experiments. We now wanted to see if including a first step in which trade can occur also enables cooperation. So in this first step, the agents can choose their participation in their own rewards, implicitly also determining the participation in the others. This successfully enables the agents to divide their tasks, and they learn role strategies within and across experiments which are stable. We are proposing a new method for the coordination and cooperation in shared multi-agent environments, namely the participation in rewards of other agents via trading of shares. This participation approach works well in the tested social dilemmas. However, it remains unclear whether agents are always able to find a stable participation. As an outlook, we would like to test other environments and maybe also with more agents, and then see if an extension with a broker that sets prices according to a limit order book could also enable cooperation. If you're interested in our research, you can also have a look at our 2 main references, which are listed on this slide. Thank you.